demonstration up here, and what I'll have you do is kind of swing around the table like this. Magic crystal here, and you put this magic crystal on the page here. It's right on top of the word birefringence. What I'd like you to do is look straight down on it. You may have to use like one eye. We'll see. So it's not looking. If you have trouble, just cover one eye. Then we'll take the polarizer, and again, this polarizer's got the transmission axis marked. So right now the transmission axis is vertical, now it's horizontal. And I've got a couple little stripes on the page here to kind of guide you. What I'd like you to do, look first without the polarizer, see what you see. And then hold the polarizer over and switch back and forth between having that transmission axis vertical and horizontal and see what you see. And then we'll talk about that. So, you want to swing around this way, and we'll take a couple minutes just to take a look at the magic crystal. And see what happens. So again, we'll look first without the polarizer and then with the polarizer. And just rotate back and forth with the transmission axis and see what happens. Hopefully you saw something relatively odd.
Oh, no. You didn't see a change?
You didn't see anything? What? You weren't impressed? You did not see it? Yeah, jumping back and forth? If it doesn't jump back and forth, let me know. It's possible the magic wore out. You saw two images first.
Yeah.
So what you should be seeing is two images without the polarizer. And depending on which way you've got that transmission axis, you'll see one image or the other image of the two. It's almost like you can filter out those two images. Yeah, that's coming up next. A little bit later.
I'll be back quick.
Okay. Okay, so you see two images.
Mm-hmm.
You see one. You see one.
I really don't know which one.
It's like, it's
Oh, that's pretty good.
got it, nice.
I've only done two of them.
So what's up with that? By the way, that's a calcite crystal. Calcite's pretty good with this. We had talked about how light goes through material and how the heck it can go in 3 times 10 to the 8th meters per second going in, appears to be going slower going through, and then it seems to be back up to 3 times 10 to the 8th by the time it goes out. And what we talked about was that interaction of the electric field component of the electromagnetic wave of the light interacting with the electrons in there, and through that absorption re-emission process where those electrons will absorb, wiggle back and forth, re-emit that light. That process takes a little bit of time, and that's a little bit different for different materials, and we can get a measure of that by measuring the index of refraction, which was the apparent speed of that light through the material compared to the actual speed of light. So again, we could categorize materials based on that index of refraction, gave us a sense of how that light's working its way through. And then we saw if we knew what the index of refraction of something was, we could then figure out exactly how much light's going to bend when it crosses an interface between two materials of a different index of refraction. And we saw that Snell's law will tell us exactly how much that will bend. We did some things with kind of a qualitative look with that, that if light goes from a lower to higher index of refraction material, it's going to bend towards the normal line. And again, those angles in Snell's law are measured from that normal line, the line perpendicular to the interface. What's happening with something like calcite is a material property that gets really interesting in some upper level classes. Not all materials have the same material properties in all three dimensions. And calcite is one that can have some properties that are different, say, in the x direction compared to the y direction. What actually happens is there's a slightly different interaction with the light in the two directions. And what ends up happening is it's as if there are two different indices of refraction in that material, depending on which direction you're looking at. So when light comes into there, it can actually bend in two different amounts, which is why you saw the two different images. And what's really interesting about the calcite is the way that those electrons are doing things this way versus this way actually polarizes that light either this way or this way, which means you can see that with the polarizer, that each of those two images is actually polarized one way or the other. If you have the transmission axis lined up with the way it's polarized, you'll see that image, but the other one gets blocked out. Of course, if you flip that, the other one shows up. So kind of an interesting behavior. That is referred to as birefringence. It basically means there's like two indices of refraction in that material. And it comes from the fact, again, that material doesn't have the same properties this way as it does this way. So there are a lot of other really interesting things in material science that look at that, the fact that properties don't always have to be the same direction or the same in different directions. So there's one kind of cool example. So I'll touch back on that. Okay, back to where we left off. So before we took our little break, we talked about images formed by mirrors, and then we had gotten into images formed by lenses. In both cases, we had a couple ways to try and figure out what images might look like. Kind of a qualitative way using ray diagrams, so we could get an idea based on what type of mirror lens we had and where that image was relative to a focal point. We could sketch three particular rays coming off our image that we chose because we knew what they were going to do once they hit the mirror or the lens, and based on then where the reflected or refracted rays ended up, we could figure out where the image was going to be formed qualitatively. So as a simple example, if I've got a lens like this, where here's the focal length on each side of the lens, here's my image, my object, and I want to figure out what the image is going to look like. Three different rays that we can choose that are coming off the tip of this image that we know what they're going to do when they hit this lens. And it does help to do them in these orders. If we pick the ray that's parallel to the optic axis first, once that hits that lens, it's going to bend and go through a focal point. All we have to do is make sure we know what kind of lens it is as far as which focal point we're going to go through. If it's a converging lens, we've got to make that ray converge. It better go down to that one. And we'll take a look at the other example here in just a second. Once we've tied up one focal point with our first ray, we can use the second focal point to guide us on selecting the second ray. So we just used this one. So now that tells me my next ray, I'm going to have to do something with this guy. So that one's going to guide me to which which ray to go. So all you have to do is lay a ruler from that focal point to your object. And okay, I've got a ray then coming off that object. In this case, it's through that focal point. Once it hits the lens, we know that one goes parallel. And then the third one's the easy one. We're going to send a ray right through the center of the lens. That one just keeps going straight through. Notice that even though we know there's refraction occurring in both interfaces here, because I've got a difference in index of refraction across this interface, a difference in index of refraction across that interface, we can simplify our picture just by assuming all of the bending occurs at one time right in the center of the lens. So that's why I do this little dotted line right here, even though that's not where it really happens. We can use that as a guide to simplify our picture. So we bring this in, bend it right at the center, just one bend completely that would give us the total refraction that we would have got across those two interfaces. At that point, what we can do is then, now that we've got our rays, we're going to take a look at just the refracted rays, the ones that went through the lens. And it helps sometimes to darken these up or use a different color or something. There's a refracted ray, there's a refracted ray, there's a refracted ray. And what we're looking for is where do all those three cross? Oh, that's right here. That identifies where the image of this piece that we took those rays off of initially, where that image of that part of the object ends up. So that tells me if this was my object, then the tip of that flame has to be right here, and everything else goes from there to the optic axis. It's just in this particular case, it's going to flip it upside down. So here would be my little flame, here's my little candle, and I need to make sure these two faces are, of my object and image are still right here at that optic axis. So just as a quick check, let's say I've got this case right here. Now I want to figure out what's the image going to look like here, where is it, what's it look like. So we'll take that first ray that's parallel to the optic axis. Actually, first I'm going to mark the center of the lens. Draw a ray parallel to the optic axis. And I know that's going to bend, and I know a focal length is going to tell me, or focal point is going to tell me how much it's going to bend. Which focal point do I use though? Because I've got two of them. Need to know what kind of lens is it. Is this a converging or diverging lens? And how do you know? The easy way.
It's thinner in the middle than this.
Thinner in the middle, that's a diverging lens. This was fatter in the middle, it's a converging lens. If it's fatter in the middle, I better have these things converge, come together. If this is fatter on the end, skinnier in the middle, I know it better diverge, I know they better spread apart when they go through. That tells me, oh, for me to spread it apart, I'm going to use this focal point to tell me just how much it's going to spread apart. So I laid my little ruler on there, line these two up, and it's going to spread about like that. I've tied up that focal point. That means my next ray has something to do with this one. So again, all I have to do is take my ruler, lay it on there from my object to that focal point that's my guide. That's just guiding me into which one of these rays I'm going to pick. So that says I want this ray. I line that up. I want, of all my choices, I want to pick that ray that comes off like that. So I send that to the lens, but it hits the lens before it gets to that focal point, so now what? That ray guided by a focal point, let me back up. The ray that's parallel refracts in a direction guided by the focal point. A ray that's guided by the focal point, what does it do when it hits the lens? It goes parallel, so that goes off this way. Switch colors. So here's my refracted ray. Then the third one, again, that's the easy one. I just send a ray right straight through the center of the lens. Here's right straight through the center, and that's just going to keep on going. But I'm going to change colors for the refracted ray. So the green ones are the ones I selected off the tip of this object. The blue ones are the ones that are refracted through the lens. It's these blue ones, the refracted rays, that are going to guide me into what this image is going to look like. So I want to know where they cross. So what does that mean when I look over here and go, wait a minute, they don't cross over here? I'm going to still contend they do cross, even though they spread out over here. Now what? Yep, that's when you extrapolate them backwards to the other side. By the way, that's harder to do than you know freehand. One actually turned out pretty good. And notice I get all three of those back extrapolations to cross right there. So what does that mean? Here's where I picked my rays off of my object. That means that is where the tip of the flame of my image is going to be. So that's right here. And then everything else just goes from that little tip down to the optic axis, in this case, that. So I had an image now that's upright but smaller than what the object was. Another bit of terminology to be aware of is, notice in this case, my actual refracted rays are touching my image. That's referred to as a real image. In this case, my actual refracted rays don't touch the image. My image ended up back here somewhere. In that case, if the actual refracted rays don't touch it, that's referred to as a virtual image. So same concept that we ran through with mirrors, this is just the lens version. Big thing to remember between lenses and mirrors. Lenses, those rays are going to go through. Mirrors, those rays are going to reflect. So just watch that. If you have a mirror, make sure they bounce backwards. If there's a lens, make sure they go through. Other than that, they're very, very similar. We saw with mirrors that we could quantitatively figure out what images would look like. We could actually calculate them and tell exactly where, exactly what they were going to be like. We do the same thing with mirrors. It's the same equations we had before, right here. The same sign conventions we had before, as long as you do it this way, with the distance to the image using this real and virtual version. Then the sign conventions are identical. So as an example, let's try one here, see if we can calculate and figure out what an image might look like. So let's say we've got this case. Let's do this picture here. Let's say we've got a focal length of 10 centimeters. Let's put this 30 centimeters away from the lens. And just to be careful when you're seeing these measurements here, distance to object, distance to image, those are always from the center of the lens or mirror. So let's say we stick that object 30 centimeters out here in front of that lens. And with that information, can we locate and describe the image formed by that lens? So first thing we need to do is figure out where it is. So where did that image end up? So we'll locate that image, so I just have to rearrange this to solve that for where the image is. So that's 1 over the focal length minus 1 over distance to the object. Let's put our numbers in, but being very particular about the signs on these, the pluses and minuses. So focal length with 10 centimeters. Is that plus or minus? What kind of lens do we have? It's a converging lens. So is that plus or minus on that focal length? It's plus. Minus 1 over distance to the object. So we're 30 centimeters away from the lens. Is that a plus or minus 30 centimeters? Is our object in front of the lens or behind the lens? It's out there in front. So that's another plus. Which, if I do just this part, is 2/30. But again, we've done these kinds of equations when we dealt with capacitors, done these kinds of equations when we dealt with resistors. no, that's not our final answer, we have to flip it over. I don't want 1 over distance to the image, I want distance to the image. So we'll flip that over. This ended up to be a plus. And we end up with a plus 30 over 20 gives you 15 centimeters. So there's one part of our numerical answer. Next, we'll figure out the magnification. That's minus from the equation. Distance to the image over distance to the object. So distance to the image, there it is right there, that was a plus 15 centimeters. Distance to the object, that was plus 30 centimeters. Altogether, we end up with this. Notice the units cancel out. And what this is on magnification, it's essentially like a times. And we've got a second number that we've calculated. So from that, can we describe this image in words? Where is it? That far from the lens. Which side? What does that tell you? It means it's a real image, which means the refracted rays are touching it. And if it's a lens, the rays go through the lens. So the actual refracted rays are on the right-hand side. And so this will be 15 centimeters to the right of the center of that lens. How big is it? What does that mean? Half as big as the image was. It's 0.5 times the size of our object, I should have said. So it's half the size of our object. How is it oriented? Is it right side up or upside down? What does that part tell you? Oh, it got flipped upside down. And notice in this case it's upside down. The reason this doesn't look half the size is that's a slightly different problem. Notice here the distance from the object to the focal point is a little bit shorter than what that is. If I move this further out, that's going to start to shrink this up. Again, we can calculate exactly what it's going to be like based on what that is. Any questions with that? How about this? Do this one for me real quick. If I've got a converging lens and put my object an infinite distance from the lens, and by infinite in real terms, infinitely far away relative to the focal length of that lens. So for us, we'll just say our object is an infinite distance away from that lens. Where is the image formed? And yes, there will be an image, by the way. But where is it formed? Again, if we've got an object that's an infinite distance away, so not 30 centimeters, but an infinite distance away, and a converging lens, where's the image formed? You can do that in your head really quick. And yes, there will be an image.
I think what's going to happen is that it's going to be, the image formed is going to be infinitely far away from the focal point as well, isn't it?
Nope. calculate it.
The distance, the object is infinitely far away.
Yeah, so where's the image?
What does that stand for?
Focal length.
Is it just in the lens?
So what's the distance to the object? What's this term? Thought I heard it. Zero, right? Where's the image formed?
The focal point.
At the focal point. Which gives a really easy way to get a good estimate of focal lengths of converging lenses. Because the image will form right at focal length if your object is far enough away. I'll show you this. This looks a lot cooler when it's bright and sunny out, but we'll try it today anyway. If we get a bright sunny day, maybe we'll try it again. I've got a bunch of converging lenses here. If you want to come up and grab a converging lens, and we're going to use these pieces of paper as a screen. Grab a lens and a screen, and we're going to head out this way. Nope, I'll let you guys pick. So grab a lens, and if for some reason we run out, you've got converging lenses at your table too, so you can grab one of those. And we're gonna go out this way. Again, it'll show up better in bright sunlight. But see if you can get an image to form. And when you do, that distance from the image to your lens is the focal length of that lens.
What is it upside down?
No, you're trying to cast an image onto the screen, not looking through the lens. So you can look at your piece of paper. So move your lens so you get the paper.
Oh.
Wow.
Oh, that's weird.
Yeah, you just do that.
And by the way, notice it's a single converging lens.
Yeah.
You notice anything about the size? All right, so the orientation of your image. Give you guys a problem here and see how you do. Let's see, what about if we had this set up? Say I've got two lenses, not one. And stick an object out here. Let's make that object 15 centimeters from the first lens. Let's put the two lenses 20 centimeters apart from each other. And let's make them different focal lengths. Let's say the focal length of the first one is 10 centimeters. The focal length of the second one is 20 centimeters. With that, describe the image formed by this two-lens system. In other words, where is it? How big is it? Is it right side up or upside down? See if we can calculate this and then put back into words a description of what the image looks like. So I know it's been a week, so I'll give you the one little tip that we mentioned briefly before of how do you do this when you've got multiple optical elements, two lenses or a lens and a mirror or something like that. Do what we just did with these equations and all this stuff with the first lens as if the second one isn't even there. You'll get an image for the first lens. Then the image of the first one will act as the object for the second one. So we'll do that again, but now we've got a new object. If there was a third one, whatever image was formed by the second lens would be the object for the third one, and just keep going like that. See what you come up with on that one. I'll give you a few minutes here to work on that. I'll give you some final numbers here to see if you did it right. Then we'll talk about later what this means. Hopefully you get to there. We'll see what happens. In case you're wondering, here's partway through. So that's what should have happened. Oops. Sorry.
What
Negative.
about the focal point, like 2? Would you have to like,
Has a focal length of 20 centimeters.
It's 24 over 3, it's a 6, 7.
Is everyone okay at least to here? That's just a straight single lens problem. Hopefully that part's all right. Now what do you do to get to
Yeah.
that?
That makes sense.
So as you're working on it, what does this mean? So if you do just lens one, it said lens one just by itself, if nothing else was around, would have made an image 30 centimeters. That plus tells me to the right of lens one. Well, where is that? That's 30 centimeters that way. Here's 20 centimeters, that puts it over here in this region. Now that we jump to lens two, again, all these measurements and those equations are from the lens. How far is now our, so this is the image formed by one, oops, I should say lens one, which is gonna act as the object for lens two. So how far is the object from lens two? How far away is it? 10 centimeters. Which side? Whoops, it's the wrong side, but we can handle that right there. Notice our object is on the wrong side of that lens, it's behind the lens. But that's where that guy comes in. So again, notice it's 10 meters or 10 centimeters from the lens we're interested in. And we can handle it being on the wrong side. And hopefully that gives you this. What do you do with the magnification then?
Because you only do 30 minus 20. Oh, because
So that's just dealing with lens two, with this being the object. So yes, this is where the final image is, but what happened with the magnification? This is how much lens two magnified that. But lens one already magnified So to get the total magnification, just multiply these together. So lens one made this thing twice as big as my original. Then lens two did that to that thing that was twice as big. Or to make it simple, find the individual magnifications of each lens, multiply them together to get the grand total magnification that you get. And so if I multiply the -2 of the first lens times the plus 0.67 times the second lens, I get that guy. So let's then, everyone okay with the numbers? So let's put that into words. So where did my image end up? You have to be a little careful with the wording here. Got a number here, but where is it?
Between the two.
Remember how we did that? We did the first lens, we ended up there. Now all we're doing is the second lens, and we have that spit out. That's 6.67 centimeters from where?
The
Second lens, that's where we just got that number. To the right or to the left of the second lens? To the right.
So in front or behind just depends on where your object is?
As far as this part, the plus and minus on it?
Mm-hmm.
Yeah,
Okay, so,
that's this part.
okay.
We found an image that was, this is relative to lens two, so it's 6.67 centimeters. That tells me it's a real image, so that's where the refracted rays of lens two would have been, which is on the right of the lens, because rays go through lenses. Okay? How big did it end up? A little bit bigger than our original object, about one third bigger. Right side up or upside down? Our final version ended up upside down. In other words, our single lens flipped it, and our second lens left it in that same orientation it was just in, which is still flipped. Any questions on that? So again, you just go lens by lens or lens to mirror, just one by one, where the image of the first is the object for the second. Okay? That's about as hard as they get. Before we take a break, I want to talk about some other peculiar things of lenses and some ways around these peculiarities. The first one is just a physical issue. So here's a big fat lens right here. That has some potential issues. Just again, these are just real physical issues, especially if I need to make a really big lens. So a classic case would be a lens that you make for, say, a lighthouse. So you have a huge beam, you need a huge lens to focus that beam so those rays don't spread out like this. They make a nice parallel beam that you can see way out in the ocean. So you could have a big fat lens. That's got a few problems. One, it gets pretty darn heavy. Two, glass actually is not a true solid, and over time it actually flows. So when you're this big, you could have some issues with that. There's a really interesting way around that physical problem for big fat lenses like this. In case you haven't noticed, the bigger the curvature of this lens, the shorter the focal point. So I can change that focal length by changing that curvature. But I'll show you how you can get around this and what they actually do with lighthouse mirrors. I'll show you some simple little examples here in just a sec. So let's take a look at that lens like this. Let's look at a cross section of it. Here's my big fat lens. And let's see how light is being refracted through this. Is that a converging or diverging lens? Yeah, big time converging, really fat in the center. So here comes a ray like this. Here's the line that's normal. To that let me change it, sorry. Let me do the ray the other way, sorry, my mistake. Sorry about that. Let's send the rays this way, sorry. So air out here, glass right here. Do I get any refraction right there? And why not? I'm coming right along the normal line. So I'll continue right along the normal line. But right here, I will get some refraction. There's the normal line right at that part of my surface. I'm going from the glass to the air, so from high to low index of refraction. So instead of going straight, I'm going to bend away from the normal line, so I'm going to bend it this way. If I look at another ray over here, I'll have the same kind of thing. And sure enough, my rays are converging. Where is all of the refraction occurring? It's all right at this outer interface, right? So what's the function of all this thick chunk of glass right here? What's the really only function of all that thick glass that's in there? No, not even that. It's even less important. They got a whole bunch of glass inside there. All that's doing is giving me that curvature I need. Which means, would I change how this functions if I did this? Let's start cutting some chunks out. Let's make some chunks like this. Take all of that glass out. Would I change how much my rays refracted? Nope, I still have that curvature in me. Even better, everyone see that okay? Even better, now that I've taken all that out of there, what if, and again, this is a cross section through here, what if I then took each of these little slices and slid them down? So I had something, I can draw it right below here. So I had something that now looked like this. I'm trying to change that curvature as I go. Notice again, if I take a ray of light, send it up this way, I still just hit that exact same curvature here as I did with that big old chunk of glass. But now it's really flat. And I've taken away all that stuff, flattened it out. Some of you have seen these before. This is a French guy, so I think it's actually pronounced Fresnel. If you've never seen one before, or you may not have recognized it, again, this is a slice through it. If I took this thing and turned it that way, it looks like little circles. Like old vans used to have that, I think. So again, if I turn it this way, these little slices look like little circles. Here's actually a simple example of it. So I got some cheap ones here. These are converging lenses that magnify, except they're flat. You can actually see the little circles. How many of you have seen this kind of thing before, now that you see that? So all those are converging lenses. It's just kind of an interesting way to flatten them out, but still get that curvature you need to magnify. So that's how you can take care of that. There's two other issues with lenses. One is called, well, let's see what the issue is, then we'll figure out what it's called. Let's say I've got a lens, and I look at the rays going through there and how they're going to focus. But I've got a slight problem if this is truly a spherical lens. I don't remember which way these usually go. Is they don't cross in the same place. What that's called is spherical aberration. And I'll show you what that actually looks like through a lens. A way to correct for that is don't have these exactly spherical. You can distort them a little bit to get these guys all to converge at the same spot right here. So you have slightly different curvatures. So a spherical lens has the exact same curvature all the way around. If you have one that's not quite spherical, you can actually adjust that and get things to focus right. And the other major aberration you run into is this one. Is if I look at light coming into a lens that's not monochromatic. But actually has different colors in it. We have a slight issue. We talked about this before. Because the amount that light bends depends on the index of refraction. Really, it's the difference in index of refraction across interfaces. But we talked about what happens when we have different wavelengths sent through there. And you all, I'm sure, did that take-home lab last week. And so you got a chance to see that in that take-home lab. What happens when you send different colors in there? Do they all bend the same? No. Which one bends more, which one bends less if we're talking blue and red?
Blue generally bends more.
Yep, blue bends more, red bends less. So instead of having a nice sharp focal point here, you start to get something like this happening. There's maybe where the blue focuses, here's maybe where the red focuses, and maybe you've got the whole Roy G. Biv across there. You end up, again, with not a nice sharp focal point. There's a nice way to fix that. What this is called is chromatic aberration, of course. There's color. Here's a way to fix that. So if that's an issue in your application, and a lot of science applications, you might need to make sure you don't have chromatic aberration issues. You can use a lens to accomplish what you're trying to accomplish. That's called, and what does this mean? Either an achromatic or an achromatic lens. What does that mean? What's that word mean? See, take that class. It's a great class. You learn all kinds of stuff about what these words mean. And try and draw this. It's a lens that's not going to have chromatic aberration. And the way it's going to do this is we're going to combine a converging lens and a diverging lens with the right curvatures so that this happens. Try and draw this. So here comes my blue, and it's gonna bend more. Here comes my red, it's gonna bend less. But what happens when these hit a diverging lens? So far I have my colors split apart. Not so good. Now what happens? My blue will bend more, and if I match this right, my blue will bend more. My red, I didn't quite draw this right, less. What I should be able to get these to do if I did this right, maybe out there somewhere, is get these to come back together again, so when I get this focal point, they're back together. So I spread them with one, put them back together with the other. And by adjusting the focal lengths of these, or in other words, the strength of these, I can get these rays to either converge or diverge the way I want. But when the combination focuses, I've got my colors back together again. I'll show you what this looks like, these aberrations. And when we get through this, we'll take a break and we'll spend the rest of today working on the lab. And I've got some things on your tables there for this lab. We're going to actually measure focal lengths, so we'll get some images and look at, see if we can figure out the focal lengths of these lenses on your table based on where the images are. But what I'd like you to do as you're getting ready for a break is I've got two little demos here that show spherical aberration and chromatic aberration. So the spherical aberration, if you don't see either of these very well, let me know, because I can make it stand out a little bit more. So these are thick converging lenses. When I stick this one on here, when you look down on it, what you're going to see is that the straight lines on this piece of paper don't look so straight through the lens. They look curved. Again, if you don't see that very well, I'll show you a more dramatic example of that. So again, especially around the edges, you'll see the lines start to curve a bit. The chromatic aberration one's kind of interesting. I've got this lens sitting on a piece of paper that says chromatic aberration. Either look right along the very edge of the lens, or if you don't quite see it, start to lift up a little bit. And look around the edges of the lens and the edges of the lettering, and see if you start to actually see colors. So notice that's just black on white. But this one has enough chromatic aberration that you can actually start to see like reds and yellows and blues if you know what you're looking for. If you don't see it though, let me know. So while we do this, we'll swing by, take a look at spherical aberration, chromatic aberration, and then we'll have a break, and whenever you're ready, we can start on lab activity and finish up today.
You didn't completely shut up.
So again, one, you'll see the lines aren't really straight through the lens, so the image is curved. The other one, if you look carefully, you'll start to see colors coming out of the edges of where the black meets the white.
I can't remember the last time I got one of those.
And again, if you lift it just a little bit, it shows up.